Hello, and welcome to part 2 of the protein assignment videos. In this video, we're going to cover additional triple resonance experiments that can be used to assist an assignment, as well as how to use NOESYs for backbone assignments. So previously we had covered using the HNCA and HNCACB going forward and going backwards using strip plots to sequentially assign your protein. However, in many cases, you might have instances where you don't have an I-1C beta. So looking at the setup I have here, I can see in this scenario, I have an I-1C beta. Here we go. Here's a good one. We can see here that I have an IC alpha and an IC beta, but I do not have an I-1 C alpha or an I-1 C beta in the HNCACB. I do have an I-1 C alpha in the HNCA here. But this makes a strip plot difficult because there may be multiple matches to that C alpha. There may be instances as well where your C alpha or your C beta is actually overlapping, and that's why you don't see the I-1. So in these instances, it would be nice to have an experiment that exclusively showed the I-1 peaks for the C alpha and C beta. And there are experiments that do exactly that. So going back to the HNCACB, you can see again, this covers the amide correlation to the I and I-1 C alpha C beta. But there are experiments such as the HNCOCA, where magnetization is transferred through the carbonyl and then to the alpha carbon. And in this way, you are exclusively going to see the I-1 C alpha. And so they have an example here of what it would look like. And each of these would be one strip. So in your strip, you should see only one peak. Now, there's also one for C betas, for the HNCACB, sorry. And that's known as either the CBCACONH or HNCOCACB. And same ideology, going through that carbonyl, but this time you're looking at both the C alpha and C beta of the I-1. And in this case, you'll have two peaks correlating to your I-1. So I have an example of that here for this data set. Let me inverse this color. So if we look here and use this as an instance, we can see we have our I-1 C alpha and our CBCACONH that shows up. And you can see it shows up actually quite stronger than the HNCACB. And there's no C beta. Let's find a better example. So this is actually poor resolution. Let's look at this one. So if we look at this example, you can see that you have the I-1 C alpha here and the I-1 C beta. Now in a CBCACONH, both peaks are going to be positive, unlike the HNCACB where the C beta is negative and the C alpha is positive. And you can already see the usefulness. In this instance, it might be a little difficult to determine which C beta is actually the I-1. They both seem to be a similar intensity. And ignoring the HNCA, you have somewhat of the same issue with the C alpha. But using an experiment that exclusively shows you the I-1 peaks makes this a lot easier. It becomes immediately obvious and apparent which peaks are the C alpha and C beta, and you no longer have to worry about intensities or overlapping C alpha C beta peaks when you're analyzing your data. So these are quite powerful experiments that can be used to resolve these issues. Now, how would you use them in a strip plot? Well, there's the added benefit that the CBCACONH only shows I-1s, and therefore you will get less matches than if you searched, for example, the HNCACB. So the way this would be done is if you were trying to go forwards, you would search the CBCACONH. If you were trying to go backwards, you would search the HNCACB. Let me show you how that's done. Say, for example, this peak that we have right here, we want to find its I-1. So you could use the HNCACB if the peaks are there, or you could use the CBCACONH. And you do exactly as before. You pick both peaks, you bring up your strip plot, and then this time you search your HNCACB here. You click peak, you click match, and there are no matches here. Sometimes if you have a slight shift in your spectra, as you can see here that I sort of do, see how the C alphas don't perfectly line up, and the C betas don't perfectly line up. There's a small referencing issue here. You can either correct the referencing for that, or I'm just going to cheat and make my carbon tolerance here a little bit wider so it looks for a wider range. And we can see here we have a match. This is the I, and we have a match here for our I-1. So this is how you would traditionally do it using the HNCACB going backwards. And this only has the added benefit that it shows you exactly which one is the I-1. However, as I said earlier, one of the additional benefits is you can exclusively search I-1s by going forward. Or sorry, I+1s by going forward using the CBCA, and that will get you less matches. So in this case, you pick the I peaks that you want to, or the I peak that you want to search, and you search your CBCACONH, and so now we're going forward. So we'll click peak, and we'll do match, right? So in this instance, I have two matches, right? Let's look at what would happen if I searched the HNCACB instead. So if I pick, match, so you can see here that I have two matches that end up showing up here. You have my I and these two matches. So let's get rid of this I here. But you might have noticed if you go back and look at the previous strip plot that I did searching the CBCACONH, that I didn't actually get these two matches. And if we go down and actually look at these strips, right, what you'll notice is, let me zoom out a little bit so you can see, that this peak is matching with the I of this strip, when it should be matching with the I-1, right? And if we look at the C alpha here, we can see here, there's probably a peak underneath here that's matching with it. But you can see here that this one does match. It is the actual I-1. So this match, or either of these matches, don't quite make sense. However, when searching forward through using the CBCACONH, we were able to find matches that actually made sense, that were the I-1 of that strip. So just to do that again, and let me click CI here. So you can see in this instance, here they perfectly line up. And because we're searching the CBCACONH, we know for a fact that these are the I-1s of the strips that we are looking at. And so in many instances, when you search an HNCACB, you might get I matches, you might get I-1 matches, where it simplifies things if you search just the CBCACONH. Now there's one other experiment that I wanted to focus on as well that exclusively looks at I-1s, and that is the HCCO and H. Let's click on that. Let's look at the carbon version, the CCCO NH. So this, like the CBCACONH, shows you only the I-1 carbons. But in this instance, it shows all of the I-1 aliphatic carbons. And what I mean by that is it might actually be better to look at this list here. So this shows the chemical shifts of all of the chemical shift ranges of all of your aliphatic carbons for each amino acid. You'll notice we've been looking only at alphas and betas, but many amino acids have gammas, deltas, and some of them even have epsilons. And these each, you can see, have unique chemical shifts. And so what the CCO and H shows is those extra carbons, the C gammas, the C deltas, the C epsilons. And so sometimes you'll get only your C alpha, C beta for, say, aspartic acids that only have those two atoms. You can get C alpha, C beta, and C gammas. You can get C deltas. So this can be really useful in identifying what type of amino acid your I-1 is. So let's look at the same example we were looking at before and look at the the CCO and H experiment here. So we can see here we have our I-1 C alpha and our I-1 C beta. Now, just going based off this value, you have something at around 58 and 36.7. If I bring up the list, let's zoom in. I hope that's visible. You can see here that there's a number of potential matches we could have with a C alpha at 58 and 36, right? You could have leucines maybe, tyrosines, aspartic acids, asparagines. However, if we look at the HCCONH, there are additional peaks, right? We have a peak here at 24.7, peak here at 14.9, and a peak at 10.2. And now it becomes extremely obvious what amino acid the I-1 is. We have 1, 2, 3, 4, 5 peaks. And so if just looking at this, you can see there's only isoleucine and lysine that contain 5 peaks. And if we look at the ranges at around 10 and 15, that corresponds to isoleucine. One at 25, corresponding to isoleucine again. You have the C alpha and C beta that correspond to isoleucine, although the C alpha is a little bit low. So this can be incredibly useful for identifying what the I-1 amino acid type is. Additionally, it has the same benefits the CBCACONH has. I personally find it particularly useful for determining glutamate and glutamic acids, since their C alpha and C betas oftentimes overlap with histidines and methionines and cysteines. And same for arginines as well, because their C alpha, C betas overlap with the ones that I just stated. Using its gamma and delta can be very useful to determine whether it's an arginine or any of the other 5 or 6 that I just discussed. So these experiments can be useful in helping assist you in your assignment and making your life in general easier. Now, there is another experiment that I wanted to discuss. And so far, we've been looking at the carbons within the side chain, right? The C alphas, the C betas, the C gammas, deltas, epsilons. However, you can use the carbonyl as well. So if we go here, there's an experiment called the HNCO. And what this correlates is the amide nitrogen to the carbonyl carbon. And so as you'd expect, or sorry, the I-1 carbonyl carbon. And as you'd expect, in each strip, you'll see only one peak. Now, there's no table of ranges here, and so the chemical shift value is not entirely as important in helping you with your assignment. But this experiment has a few advantages. So let me open it up here so you can see it. One advantage is it is one of the most sensitive, or I think it is the most sensitive triple resonance experiment. And so as a result, sometimes when you have poor resolution in your NHSQC, you can determine this by using your HNCO. Right, so in this instance, if I go here, all right, the resolution is sometimes not so great, but you can see that there are different carbonyl values for these peaks. So if these peaks were, say, for example, on top of each other or overlapping, I could be able to determine which one is which by using the carbonyl itself. So how do we use the HNCO to assist us in our actual sequential assignment? So as we've seen here, in many cases, you need an experiment that shows you the I and I-1 so you can connect them. The HNCO shows you the I-1, but there is an experiment that shows you both the I and I-1 carbonyl. And that experiment is known as the HNCACO. So this correlates the amide with the I and I-1 carbonyl. Now, as you might expect by just looking at this, the I carbonyl is going to be stronger than the I-1. So you can see that in this example here. Now, I don't have an example of it because in this data set we didn't run an HNCACO. However, the theory is very similar to all the experiments we've seen so far. You're able to go forwards and backwards using your carbonyls if you have these two pairs of experiments. So for example, if you wanted to search for the I-1 amino acid, you would use your HNCO peak and you would search the HNCACO. So for example, I would pick my HNCO, I would do a strip plot, I would go to show, and I'd pick, like I said, I don't have it, but I would pick the HNCACO to search. And that would be searching using the I-1 carbonyl. You could do the reverse. You could pick a I peak carbonyl and search the HNCO for a match. So you've seen using these triple resonance experiments, we can use carbonyls and the aliphatic side chain carbons using a variety of experiments with strip plots to search for I-1 and I matches. That'll enable us to go both backwards and forwards for sequential assignment. However, I wanted to discuss something different this time, and that is to look at the hydrogens. So if I bring this sheet here, you can see that hydrogens also have their own unique chemical shift ranges depending on which amino acid you're looking at. So alanine betas are a little bit on the lower end here, along with, say, leucines. In this case, histidines and phenylalanines, tryptophans, and tyrosines, along with cysteine, asparagine, and aspartic acid are really unique because their C betas are in the 3 range. If you're looking at further down, deltas and gamma 2s, isoleucines and leucines are very unique as well. And so this can also be used in helping identify what type of amino acid you have. And one of the really good advantages of this, let me bring this here and enlarge it, is being able to, again, differentiate between, say, glutamate and cysteines, or glutamic acids and methionines, or um, tryptophans. These all have the similar C alpha and C beta, but their H alpha and H beta is different, right? So you can see here cysteine's H beta is at around 3, where the glutamine and glutamic acid is at around 2. So while their betas here are difficult to distinguish, if you have the chemical shifts of their hydrogens, you can easily distinguish between the two. And the experiment that shows you the hydrogen values, I don't know if they have it here actually. Right here, is the HbHACONH. So this experiment exclusively shows the I-1 H alpha and H beta. So some peaks have just one H alpha and one H beta. Some peaks have two H beta. So you can get either 2 or 3 peaks from this strip. And as stated before, the value of this H alpha and H beta can be unique enough that it can tell you what type of amino acid you have. So let's go back to this example that we were seeing before, right? We had stated that we have an isoleucine here as the I-1 based off of the HCCONH. So if we look at the HbHACONH strip for this, we have 2 peaks. We have an H alpha and an H beta at 1.8 and 4.1 respectively. So if we bring up our table here, let me move some of these over. Let me actually get rid of this, move this over. Okay. If we look at the hydrogens here for isoleucine, we can see around 4.1. That makes sense. And a beta around 1.8. That makes sense as well, right? So that matches. Let's look at an instance where the I-1 is a histidine. Okay, right here. Here we go. So we can see here in this instance, let me bring up this alpha hydrogen. So we have a threonine, and that's just based off the C alpha C beta. And it's I-1, you have a amino acid that has a peak at 52.6 C alpha and a C beta at around 30. Let's bring this here. So going purely off just the C alpha C beta, we see with those values, it could be glutamine or glutamic acid. It could be potentially a cysteine. It could be arginines. Could be histidines. So it's difficult just using the C alpha C beta to determine what type of amino acid that I-1 is. The HCCONH can give us some clues. If it was a glutamine or glutamic acid or arginine, we would expect a peak somewhere in the 30s here at like 35, or a peak a little further back for arginine, such as around 26, right, as can be seen here. But we don't have that. So that does narrow our search down a little bit. Could be a cysteine, histidine, maybe a methionine. But now we can look at the H alpha, H beta. You have an H alpha at 4.8 and an H beta at around 3.2. So if we look at methionine, 4.8 does match with the H alpha, but 3.2 is way too high for H beta methionine. So that gets rid of that. If we look at histidine, we can see that its H alpha and H beta match, and cysteine, its H alpha and H beta match. So using the, let's bring this back. So using just the H beta and H alpha, we were able to eliminate this methionine. But say we don't have the HCCONH, so we can't eliminate the arginine, glutamine, or glutamic acid using the carbon values. Using the H alpha, H beta, we can still eliminate those, right? So you can see that glutamine and glutamic acid H betas are not at 3.2. And so this experiment can give you specific hydrogen values that enable you to eliminate some of your potential options. Now, this is not generally used for strip plot purposes, but it can be very helpful in determining what your I-1 amino acid type is. Additionally, this is a critical requirement for connecting your backbone to your side chain. So when you want to assign your side chains, you need both the carbon and hydrogen values of your side chain, and this experiment gives you those hydrogen values. So it's one of the main set of experiments you would want to run if you're assigning your side chains as well. Thus far, we've been discussing triple resonance experiments that correlate the I and I-1 amino acids by transferring magnetization through bonds. However, we can transfer the magnetization through space as well with nearby neighbors using the hydrogen of your amide. And these are known as NOESYs. And specifically for the backbone, the experiment we'll be focusing on is the N15-NOESY. And this correlates the amide backbone. Here it displays I and I-1 hydrogens that are nearby. But it's not just the I and I-1 hydrogens, it's any hydrogen from any amino acid, including other amides, that are within a particular distance from the observing atom here. And this is an example of what the strip looks like. But I think this diagram is a little messy and a little confusing to try and understand right off the bat. So I'm going to take this step by step. So let's bring up Paint here. So let's zoom in on this here. Let's say in this scenario, let's draw a proton amide here. Oops. Right. And then let's draw another one right next to it, say a nearby neighbor. Oops. Okay, so now that I have these situated, so these amides from two different peaks are within a certain distance, and magnetization can transfer from one back to the other. Now let's say this is your I peak. This is the amide that you are looking at in your NHSQC. Now this I peak, let's draw a strip here. This I peak, this hydrogen, is going to have a specific chemical shift. This hydrogen that it's looking at is also going to have a unique hydrogen chemical shift. And so say that shows up over here, right? So this is, say, a nitrogen peak at 100, let me write it here, at 120.25, for example. That is the value of this nitrogen. Now this nitrogen down here has a value at 118.34. And it's of course going to have its own strip as well. So if we look at its strip, right? So say this nitrogen, this hydrogen that's connected for this backbone, it has a chemical shift here. Well, this sees this adjacent nearby amide hydrogen here, and so it also shows up as well, right? And so let me draw a line. So this correlates to this, and this correlates to this. So you can see that they both share each other's respective hydrogens' chemical shifts. And so in a large, big plane, right, you're going to have, say at 120 here, let's move it. At 120 on this side, you're going to have a peak down here and a peak up here. And then at 118 over here, let's say 118 is way over here, you're going to have a similar cross peak. So you're going to have something here and something down here, right? And you'll notice that as you look at your NHSQC, there is a diagonal cross peak. And this box that you can form represents hydrogens that are nearby, that are seeing each other, that are close in contact with one another. So that's exactly what you can see here, right? You have this diagonal strip, and these are just different nitrogens. And each strip that you see correlates to what the hydrogen of that amide is looking at, what is nearby. And so there are naturally different ranges. For example, let me zoom in. You can't see the axis very well here, but at hydrogen values between 7 to 10, normally nearby hydrogens that are attached to nitrogen, so your amides, is where they show up. Higher up here at around 1 to 2 to 3 to 4, this is where your H alphas and your H betas show up, right? So if I bring back this here, right? So your H alphas show up between 4 to 5. Your betas can show up between 2 to 4. And you can even get some methyl groups but from 0 to 1. So let's see how this actually looks in the context of the experiment and your data. So let me invert the color here so you can see it a little better. And let's go back to our classic example here that we had. And let me scroll all the way down here. So in this scenario, we have a peak here. And the I peak will always line up perfectly, right? So here, this proton is the proton that is connected to the nitrogen of the amide that we're looking at here. And anything else would be hydrogens that are nearby. So we have nothing between this 7 to 10 range, so we have no other protons that are connected to the nitrogens for the amides. You'll have something sometimes at around 4.7 or 6. This will usually be the water peak. And here we have something at 4.1. This is in range for the H alpha, something at around 2.6. This is probably a nearby H beta. And we have a methyl group here as well, probably the methyl group of this I-1 isoleucine. Now you might notice that the H alpha here lines up with the I-1 H alpha here, right? This makes sense, right? The H alpha of the nearby I-1 and I+1s, they're going to be close. And so you will sometimes see those in your NOEs. That's not always a guarantee, so you cannot use the NOESY necessarily as an absolute replacement for an HBHACONH, but you can see those connections. For example, here you have another H beta at 2.6. This is clearly not the H beta of the I-1. In fact, in the NOESY, maybe it's that small noise, but you don't really have a peak for the H beta for the I-1. So this might be the H beta for your I peak. Again, it's not a guarantee. It all has to do with how far things are from one another and a variety of other factors of whether or not they will show up. But in this example, you can just sort of get an idea of what sort of stuff show up and where. So let's see how we would use this to assign a peak. Let's look at an example here that has connecting. Here we go. So in this scenario, we have a glycine, and we can just see this from the HNCA. And we can see we have 3 peaks in the amide region. We can see one of them, the center one at around 8.2, is the I peak, so the hydrogen that correlates to the peak we're looking at here in the NHSQC. And there are 2 other peaks here. Now, these could be through space, but they also could be the I-1 and I+1 amides. Those are also close. So something that you should often look at when you're running your strip plot matches for your HNCAs, HNCACBs is see if their proton values match the NOESY values that you see here. So what I mean by that is let's look for the I-1 for this glycine. So if I want to look at the I-1, I'll use my CBCA here. I'll pick both of these. I'll do a strip plot. I'll search the HNCACB. And we'll do a pick peak, and then we'll match. So here you can see I have 3 strips that match. Now the C alpha and C betas for all 3 of these is a good match. So how can you differentiate which one is the correct I-1? So the way this can be done is by using your NOESY, right? So if we look at this peak, we can see if we hover right over it, it has a proton value at around 8.66 for this strip. We can see that does not line up with what our NOESY is looking at. So let's look at this other match. This is at around 8.34. We can see again, and again, keep in mind where you'll see the horizontal bar in the NOESY when I line these up. You can see in this scenario, that doesn't line up perfectly either. If we look at the third match here, and we line it up, we can see it's at 8.53. That is a much better match to this horizontal, to this peak that's right here. Now, as I stated, they should be connected. So what I mean by that is whatever this peak is, whatever amide peak that this is, you should also see the hydrogen of the amide of this glycine peak we're looking at. So let's go to this peak over here, right? So our strip plot has told us, based off the C alpha, C beta, sorry, this one, that this is one of the matches. Now, if we look back, our glycine was at 8.25. And we can see here at 8.25, it's a pretty good match, right? So here you have your I peak at around 8.5, and at 8.25, you have the glycine, which is the I-1, right? You can see this in another way as well. So let me put a vertical bar here. So you can see a vertical bar here. And let's go back to that glycine that we were looking at. And let's put a vertical bar here, right? So let's look at this NOESY. If I go down in the NOESY, if I go over to this where this vertical bar is, you'll see that it lines up. And if we go to our match in the strip plot, that we have here, what you'll notice is if I go to where that glycine is, the proton value of the glycine, it matches up as well. Again, these matches aren't always perfect. You know, there's some wiggle room to play around here, but this is the general idea. And so you can use your NOESYs to narrow down your potential matches. Now there is a hierarchy when you look at this. Your triple resonance experiments are always going to be priority because the NOESY can be through space. It is not guaranteed that it's the I-1 or I+1. So you should always use the triple resonance to find your matches and then simply use the NOESY to confirm or help narrow down your searches within those matches. Now there's another way you can use your NOESY as well. And that is searching the NOESY strip plot itself. If you recall, I brought up, right, within each strip, right, so this is one strip and this is another strip, you're going to have connections, right? One amide is going to be able to see the other and vice versa. And so you can actually search these in a strip plot and say what strip here is able to see this strip here as well. Which ones are basically connected. And so to do this, you pick both of your peaks and your NOESY, and then you can look at, and then you search your NOESY, right? So you do match, or sorry, peak, and then match. And here we have a couple of potential matches. We have 3 matches, right? But if we combine this with our 3 matches, right? So again, we have 123.1, 119.4, and 120. 1.4. So let's go to our notepad. Let's write down these values. So we can write down 121.4, 119.4, 123.1. So what this is saying is that every single NOE strip here, so let's bring this here, let's click CI so you can see better. Basically what this is saying is every single NOE here has a match that connects back. So it contains these 2, right? So this might potentially be searching for an I-1 or I+1. So now we used our NOE, we have 3 potential matches. Let's say we want to use the, we want to use the C alpha and C beta. So here's our C alpha. And this is the C beta. So now we're going to search the CBCACONH because we're picking the I peak and we're going to try and find its I+1, which is that glycine. So let's bring my tolerance up a little bit. Peak, match, and there's no matches, which we know for a fact there is because I've already signed this. This happens sometimes in Sparky. It can be a little glitchy and doesn't always work perfectly. So let's just use the CA here. Peak and then match. And so you can see that we get a number of different matches here, and we have a number of different values. Now you can do what I did, go through each one individually, right? Look at which one lines up and which one makes sense with what we're seeing. Or you can use the matches that you had from your strip plot using your NOE, your NOESY, to narrow down from this list, right? Looking at their nitrogen values. Now, one might think at this point, well, wouldn't it be nice if I could search both the C alpha, so search the CBCOCNH, look at what matches have the C alpha, and search the NOESY to see which NOESY strips have these 2 peaks. Unfortunately, Sparky does not allow you to do that. Maybe other programs do. I have created a plugin, a separate program for Sparky that does enable you to search multiple spectra concomitantly. But Sparky only lets you look at one at a time. So you can either go the way I showed through each one individually like this and see which one lines up. Or you can write down the values from your NOESY strip plot and compare them to the values in your strip plot using the triple resonance experiments. So this is one way that you can use your NOESY to try and confirm or narrow down some of the potential matches that you've gotten for your I+1s and I-1s. These are incredibly useful experiments for this purpose because you can use more than just the amide. You can use other atoms as well. Let's go to one that has better resolution. Let's go back to this glycine up here. You can see in this scenario that this glycine contains H-alphas, both for potentially itself, and you can see this lines up quite nicely with the HBHACONH, so it's I-1. You can see it has H-betas that match with the I-1. Glycine doesn't have an H-beta, so this is probably something else through space. And it even has connections to a methyl group that's through space. So let's bring up this scenario here. We said that this proton here sees this proton, and therefore you have this sort of cross-peak connection. But this doesn't just have to be true for amides. This can be true for any hydrogen value. So let's get rid of this. And let's say you have, let me use this line here. Say you have here, this connects to some, you have this here, this connects to something else that has a carbon, right? So we'll do a carbon here, and then we'll copy and paste this, right? So let's move this here. I'll just draw this last part. So each of these will have their respective hydrogens. Excuse my lack of artistic ability. So each of these will have their respective hydrogens. And this amide that you're looking at can also correlate to itself, but its nearby neighbor, right? So let's just show this as an example. It can show up with its nearby neighbor, which is what we've been seeing. And subsequently, its nearby neighbor, this guy, let me change the color of the brush here to red. Its nearby neighbor can also see the H-alpha and H-beta of, say, the I- or I+1 partners. So what do I mean by that? Let's look at our data again. So in this case, you can see again, like I said, we have your H-betas and your H-alphas here showing up in this glycine. So we can see it's at 2.17 and 3.885. Let's go to what we suspect with the I-1 for this is over here, right? So now, if we look, we can see that the H-beta and the H-alphas, if we go back and forth, right, 3.8, 3.85, right, 3.85, 3.85, they match, right? The H-beta, 2.16, 2.16, they match. So you don't just have to use the amide nitrogens, you can also use the H-alphas and the H-betas as well that you see in your NOESY. And even if you don't see the H-beta and H-alpha for your I-1 in your NOESY here, right, for the I-peak, you have it in the HACONH, right? So you can use the values that you see here, right, and compare them to what you see in your NOESY. Again, this is not concrete. The NOESY can look at any hydrogen through space, so it doesn't necessarily mean they are the I-1s or I+1s. However, you know the HBHACONH is definitely the I-1. And so if the amide matches up, and the H-beta matches up, and the H-alpha matches up, that's a pretty good correlation right there that you're probably looking at your I-1 peak. So the NOESY is really nice for assisting in assignment by basically confirming all the other data you have. I would never use the NOESY by itself because, again, it can be a little risky because it's anything in space. It doesn't necessarily mean your I-1 or I+1 neighbors. Sometimes I've had cases where I don't see the I-1 or I+1 neighbors. I see a NOESY that's nearby at another part of the protein. So I would never use this by itself, but I think in conjunction with all the other experiments you have, it's a very useful experiment. And we will discuss later how you can actually use this experiment to assign your side chains, specifically the methyl groups. For example, we can see in this glycine doesn't have a methyl group, and its I-1 also doesn't have a methyl group. Yet it sees a methyl group somewhere potentially through space, right? And if you have the structure, you can see, based off this glycine 326, what methyl groups are nearby through space and potentially assign your methyl groups using just this by itself. We'll discuss this in a later video, but for now I just wanted to show how you can use this NOESY to assist within your assignments. It's an incredibly useful experiment, and I'd recommend confirming every single assignment you have with your NOESY. So for example, I have done some assignments here, right? And let's look at another place, right? Let's use this glutamate right here. Oh, this is a bad example. This data set isn't always the greatest. Let's find a decent example. There you go, right? Here you have an I peak and you have something else here. Could be I-1 or I+1. Now I've assigned this so I can check and look at the hydrogen value of the I+1 is 8.873, so that's not it. The I-1 is 7.605, right? So you can see that it makes sense and it matches. So even if you've done your assignments already and you're already partially completed and say you get your NOESY data after the fact, this is a good thing to go through and check your assignments and make sure that the NOESY makes sense. It can be useful for identifying misassigned peaks potentially. Again, there's no guarantee that this is the I-1, but it is good confidence when your NOESY does match. So that's it for this sort of video. In the next video, we're going to be covering how to use chemical shift prediction programs such as Sparta Plus to assist in your assignments. Additionally, I'm going to discuss some of the programs I've made to sort of assist in streamlining the assignment process, such as a strip plot that allows you to search multiple spectra, such as the CBCACONH and your N15-NOESY at the same time, as well as a program that looks at anchor points and tries to find good places to start when it comes to beginning your assignment. So that's it for this video. Thank you for watching.